Hello again, I'm Phi Myers of PEMY Consulting. This is the second of the 3 tank corrosion modules. In this module I'm going to talk about how API 653 determines tank internal inspection intervals using quote corrosion rates. Interestingly, they are not corrosion rates, and this must be understood to do any serious work in corrosion prediction. Here's a pop quiz. What part of the tank is inaccessible for the purpose of corrosion measurement except during internal inspections? Well, you have access to the roof, both the outside and sometimes with a confined space entry you could have access to the interior surface of the roof. The same is true for the shell, but most of the necessary readings could be gotten from external non-destructive examination. So the answer to the quiz is the bottom. The bottom is inaccessible except during internal inspection. Here's another pop quiz. A new tank is installed 10 years ago. We want the topside pitting corrosion rate. The deepest pit was found to be 100 mils. What is the corrosion rate? Check all that are appropriate. 1 is 100 mils divided by 10 years is equal to 10 MPY. 2, it could be more or less than the 10 MPY before or after the inspection, respectively. And 3, it could be 10 MPY plus or minus. Item 1 is correct because the nominal corrosion rate is just computed by taking the depth, 100 mils, divided by the time, 10 years, to get 10 mils per year. Item 2 is also correct. The corrosion rate before the observation at 10 years can be higher than the linear corrosion rate and less than the linear corrosion rate after the inspection. And the answer to part 3 is correct. Corrosion is a stochastic process, so it's never just a fixed number. 2 identical tanks with identical conditions could have slightly different corrosion rates. These simulated points show how corrosion would actually vary with identical tanks. So we could say that part 3 is correct as well. API assumes linearity with time, and this is made clear in API 570 and in other places. But API 653 is really using an algorithmic approach. And although it's called a corrosion rate, it's not. API deals with 3 cases, as you would expect: topside only corrosion, bottom side only corrosion, and combined topside and bottom side corrosion. You can treat cases 1 and 2 identically because they're just the flip side, literally the flip side of each other. Case 3 assumes that the deepest topside pit lines up with the deepest bottom side pit. I call that the lard factor. Here we graphically see the 3 cases. So here is case 1, case 2, and like I said, the almost impossible case where the deepest topside pit lines up with the deepest bottom side pit. That would be like throwing 2 different colored marbles in a bin of hundreds of millions of blueberries and expecting them to end up right next to one another. It just ain't gonna happen. So to understand this in more detail, we need to get into the weed garden of API 653. There are 2 methods for dealing with corrosion and bottom life in API 653. The first method is optional and is called, quote, an acceptable method. However, everybody uses it. Let's look at the formula. Here we've rearranged this formula into solving for OR, which is the operating interval. You take the minimum of either the top side remaining thickness or the bottom side remaining thickness, and those are defined here. RTBC, for example, is the minimum remaining thickness from the bottom side corrosion after repairs. This is the critical part. It's not the remaining thickness from corrosion, it is the repaired thickness, and that's where all the problem comes in. The same is true for the RT-IP. And here is the lard factor I was talking about, the summing up of the stock side pitting rate and the underside pitting rate. The second method is probabilistic, which is allowed to be used in API 653. and typically that would be either similar service or risk-based inspection, RBI. It says for a probabilistic method, a statistical analysis is made of the thickness data from measurements. The sum of the maximum topside and bottom-side corrosion is the lard factor, and is the reason that many more tanks are not leaking that would be without it. Later, you will see that the basic formula we looked at earlier is always unconservative and is like a get-out-of-jail-free card. Without it, there would be many more tank leaks at the next internal inspection than there currently are. So let's look again at the two basic models. There's the API 653 corrosion rate model, which is by far the most widely used, but it's also a mysterious black box. The second method, of course, is the common sense method. It says that the linear corrosion rate is simply the lost metal thickness divided by time. The black rectangle represents a portion of the tank bottom. The pit at the top surface illustrates the maximum thinning that corrosion has caused when it is observed when the tank is internally inspected. The MRT is the minimum remaining thickness. This is the thickness to which corrosion, as calculated by the standard, may be reduced before another internal inspection is required. For the sake of argument, we'll only look at the internal pitting, but the same arguments apply to soil side pitting. At the time of the internal inspection, the deepest corrosion is measured and the time in service is known. This can be used to compute the linear corrosion rate by taking the depth in mils divided by the years in service to get mils per year as a corrosion rate. Notice that the slope represents the corrosion rate. But API has a repair to thickness. The choice of what repair to thickness to use is entirely up to the owner-operator. This means that any thickness which has been reduced to less than the repair to thickness must be repaired. If it is greater than the deepest pit, then no repairs are made, of course. Obviously, the repair to thickness is going to be greater than the deepest corrosion, otherwise no repairs will be conducted. If the repair to thickness is set to the original thickness, then the entire bottom virtually would end up having to be replaced. So some value in between those two extremes is usually chosen that presumably optimizes a tank bottom life as well as costs. The API corrosion rate is now showing with a slope or corrosion rate that is less than the linear corrosion rate. This slope is less than the linear corrosion rate. Let's back up and start over. Common sense tells you how to compute the linear corrosion rate. Reduction in thickness divided by time in years is reported in mils per year. Let's arbitrarily increase the repair to thickness as shown. Then again where we are near the original nominal thickness. This is truly magic, as I can get any corrosion rate I want simply by playing with the repair to thickness. The concept could only make sense if each XY point on the tank bottom, in other words, each unique location, had a unique and unchanging corrosion rate. This is a strong but also completely unrealistic assumption for a stochastic process like corrosion. To summarize the model, and by adjusting the repair to thickness, we can keep reducing the corrosion rate. But notice that we can achieve a zero corrosion rate. But we know from experience that just patching or replacing a tank bottom does not result in a zero corrosion rate, which is what API 653 implies. The hazard is that if the corrosion rate is low enough, as shown by the red dotted line, and under the right conditions, corrosion can cause a bottom penetration. The caution is that if API 653 is below the bounded line, then there is danger that the tank will hold through. Let's look at this in more detail. The MRT is the minimum remaining thickness and is shown by the dotted green line. This is what you are supposed to allow the tank to corrode to before setting the next internal inspection interval. So when corrosion shown by this dot hits the green line, you're due for an internal inspection. The slope of the blue line is a reduced corrosion rate based on some repair to thickness. As long as the upper dot on the blue line is occurring before the bottom holes through under the actual linear corrosion rate, there's no problem. If we lower the corrosion rate enough using the repair to thickness, this green dot under the API 653 just lines up with the actual hole through point for the linear corrosion rate. So no leak has occurred, it's just imminently about to occur here. Now this formula gives the green line. It's the slope where if you go above this you are going to have ground leakage under the linear corrosion rate model. It's a simple formula. It takes 1 minus the minimum remaining thickness divided by the repair to thickness after repairs times the API 653 corrosion rate. This is called the bounded corrosion rate, CB. This simple formula that uses the API 653 nomenclature and symbols and does not require any change to the current API 653 procedure was developed because in API 653 committee people did not want to change the long-standing procedures for establishing inspection intervals, and so we came up with a simple check to make sure that games are not being played with the repair to thickness such that the tank could actually leak. If this rate is exceeded, then the arrow shows the time that a leak would be occurring between the hole through point under the linear model and the time to take this tank out of service when the API 653 hits the MRT. If you take the remaining thickness measured from the current minimum thickness to the MRT and divide by a corrosion rate, you get time in years or remaining life. This results in the hyperbola shown by the blue line, which has been set at the bounded corrosion rate. But the API 653 method does not use remaining thickness. It uses remaining thickness after repairs. The interval is constant regardless of what depth of corrosion has reached. So it is a flat dotted line which does not change no matter how deep the corrosion was found to be. This should be of concern to you. So far we've covered two approaches, the 653 modeling approach and this linear model that you're used to and have used all your career. The 653 approach requires specialized assumptions. It's not a function in the sense that you can get many different corrosion rates just by tampering with the repair to thickness. And you can definitely never do similar service or risk-based inspection properly if you use corrosion rates from API 653. On the other hand, the linear model is a simple, practical modeling approach that's been used for decades. It doesn't make any assumptions about the internal pitting rates. There is only one corrosion rate based on the deepest corrosion rate found. It has nothing to do with the repair to thickness. It's probably conservative because we know that corrosion slows down somewhat with time. It follows a power law, and we'll discuss that in Module 3. And you don't need to use these confusion factors or what I've called the lard factor to bail you out of potential problems where hole-throughs could occur. The problem with committee work today in this area is that we don't have enough corrosion, metallurgical, and materials engineers working on this important problem of risk-based inspection and similar service when addressing tank bottom corrosion. So this is a call to action. The message to the owners and operators is that you have to have a tank database that correctly tracks the right kinds of data if you hope to be able to ever use something like similar service or risk-based inspection. It's important that we develop this properly because Standards like API 653 are necessarily conservative, and internal inspection intervals are not optimized if you don't use corrosion rates. If you are going to use the 653 methodology, then I recommend that you apply the PEMY bounded corrosion rate formula that I showed earlier, and that will eliminate the potential problems with hole through that occur under certain conditions using the 653 methodology. In having inspection reports written for you, it's important that they report the actual corrosion condition, the deepest corrosion that has occurred, so that later if you go back and assess the reports for corrosion, you don't have to rely on the reported API 653 corrosion rate, which is incorrect. Many inspection reports that I've looked at do not report the deepest corrosion or even the time of service, so it becomes impossible to use a corrosion rate to establish a method like similar service. I won't go through all the details of this, but corrosion rate databases, which could be combined with a main tank database, they need to be established and record the critical pieces of information, some of which are listed here. Finally, similar service and RBI are good tools, but they're not trusted by the regulatory industry, certainly, and not even by industry itself. That's because a black box approach has been used. Another factor is the sparseness of data, and most of it's invalid anyway, that at least comes out of API 653 inspection reports. RBI has often been used to fulfill the goal of increasing the average internal inspection purpose solely for the purpose of reducing costs without really the purpose of getting at the truth. But if you do it correctly, you can often have both. You can have your cake and eat it too. And like I said, it's badly needed because typical prescriptive methods for setting internal inspection intervals like those in API 653 have to cover a myriad different kind of tanks, and therefore a conservative approach is needed. But if you're willing to do the work of similar service and risk-based inspection, then you should be able to increase those intervals where it is warranted. Of course, in other cases, it may be that the interval decreases. Making this change is a huge one. It would take something on the order of a goal by API or NACE, or even a joint industry project to accomplish this. It requires critical upfront planning and data collection, and a long amount of time. There are sound statistical theories that can be used, such as the results by Ricker. It requires long-term thinking, so in Module 3 we'll get into this in more detail. This concludes Module 2 of the 3-part corrosion rate series for tanks. There's much more information about this on the PEMY Consulting website, so I invite you to take a look at that. It goes into all of the details and has papers related to this topic. I thank you.